Ethanol, often abbreviated as ETOH, it is more commonly known as alcohol, and you may have had some of it last night, and if you're really lucky, you might even be having some of it right now. So when we drink ethanol, our body doesn't just let it sit there, it starts to process it or metabolize it. And so the first step in the metabolism of alcohol is its oxidation to acetaldehyde. And this reaction is catalyzed, and that means made faster, by the enzyme LADH, which is liver alcohol dehydrogenase. And so let's say we didn't know the rate or rate law associated with this reaction. What we might do is we might compare some data. So the first type of data we might compare would be the rate of consumption of alcohol, and I don't mean drinking it, I mean the rate it is consumed in the chemical reaction. So we write that as negative D concentration of ETOH over DT, and we compare that to the initial concentration of ethanol. And so if we were to do that, let's say we had initial concentration of 1, and we had a rate that was here. And let's say we went all the way up to an initial concentration of 10, and we still measured the rate as being exactly the same. This is consistent with a zero-order reaction. Something useful to keep in mind or to remember is that many reactions that are catalyzed, that have a catalyst that is, are zero order. And that's because in the end the rate is simply limited by the rate at which the reactants can sort of interact with that catalyst. So our catalyst here is LADH, liver alcohol dehydrogenase, and we have found that this is a zero order reaction. But we might have been given a different type of data. So let's see what happens if we compare the concentration of ethanol to the time that has passed. So again, we're sort of marking the rate of its consumption, and I don't mean by you or me. If we were able to measure this in our bodies or something and record the concentration and the time associated with it, what we would actually get is a perfectly straight line like this. And this is also consistent with zero order reactions. So if we get a straight line from comparing the concentration of our reactant ethanol to time, that's a zero order reaction. And not only that, but we can actually find that the slope of this line is equal to the negative of our reaction constant K. So that's another useful piece of information. And so now that we know this is a zero order reaction, we can start writing some rate laws. And the first rate law that we have is the differential rate law. And for a zero order reaction, that says that the rate, which is negative D concentration of ethanol, over dt is equal to K. There is zero dependence of the reaction rate on the reactants. So that's sort of how I remember the rate law for a zero order reaction. And then the other rate law that we have is the integrated rate law. And what the integrated rate law says is that the concentration of ethanol, ETOH, at some time t is equal to negative K, our rate constant, times the time t plus the initial concentration of our reactant, ethanol. And I sort of denote that with a zero subscript with this concentration of ethanol. And then one more thing we might like to know about zero order reactions is the half-life. And we often abbreviate half-life as T1/2, and that's defined as the time at which the concentration of our reactant, ethanol, at that time 1/2, see I put that in the subscript here, is equal to 1/2 of the original concentration of ethanol, our reactant. So let's say we want to find an equation for this half-life. What we would do is we would plug the T1/2 and the concentration of ethanol at T1/2 into our integrated rate law. And so what that will end up looking like is the concentration of ethanol at T1/2, our half-life, is equal to negative K times T1/2 plus our original concentration or initial concentration, if I can spell ethanol, of ethanol. And so now we substitute in the half-life amount of ethanol into this equation. So what that means, or what that results in, is 1/2 of the initial concentration of ethanol is equal to -K times T 1/2 plus our initial concentration of ethanol. And so I'm going to bring the concentration of ethanol over to the left-hand side. So what we get is -1/2 of our concentration of ethanol initially is equal to -K times the half-life T 1/2. And then solving for T 1/2, our half-life, we get that it's equal to the concentration of ethanol initially, or just in general, the concentration of the reactant, divided by 2 times the rate constant or reaction constant K. And so this is our half-life equation, and what it sort of tells us is that if we increase the initial concentration of our reactant, the half-life increases as well. And that sort of makes sense. If you drink a lot of alcohol, it takes longer for your body to process it than if you drink just a little bit of ethanol or alcohol. So that's our half-life equation. And then we have our integrated rate law equation. And if you notice, this sort of takes the form of a line, y equals mx plus b. And finally, we have our differential rate law, which tells us that there is zero dependence of the rate on the initial concentration of the reactant. And this is for a zero-order reaction.